Hello. I recently came across this 6 port USB power supply just for a couple bucks. And let me see if we can get some branding behind this here. Just this Voltix, looks like. Never heard of them. But I thought it'd be interesting to take a look at. I'm not sure where whoever bought this got it from. Maybe online, maybe in a store around here. But it's apparently capable of 30 watts. That's quite a bit. 7 amps output. I don't know if I believe those claims, but we can take kind of a closer look. I'm not going to try to load every port, but we can test maybe the 2 amp one, and then take a look at the circuit board inside and see how they're doing stuff. So it's mains connected. I have it hooked up to my Variac at the moment, 118 volts. Let's just get that a little bit closer to 120, maybe. Yeah, let's not exceed 120, I suppose. That's probably good enough. All right, so not plugged in at the moment, but I just got one of these cheap dummy loads from AliExpress, so I thought maybe it'd be a good opportunity to use this to test this out. Of course, it's not 4-wire measurement, so it's not going to be the most accurate, but we'll see what we see on the load end. So a nice short USB cable, and let's plug that into the micro USB spot here and switch on our power. And there we go. Took a second, maybe just some delay in the electronic load, but we have 5 volts. Okay, so that's good. 5.17, no load. Let's just try to give it a little bit of load. This should be the 2 amp capable port. We'll see what we can get out of it. Voltage jumped a little bit. Okay, we're still 5 volts, doing over 1.5 amps. Voltage is kind of stuttering a little bit between about 50 millivolts. Let's keep going. So we're at 2 amps right now, and seems to be doing okay. My Variac says we're drawing 100 milliamps AC at 119.2 volts. So that's pretty good. We're at least doing the 2 amps out of that. Let's just keep going, see when it cuts out. So let's get up to 3 amps. .8 volts, that's not terrible. That's after voltage drop of this short cable too. So it's a fairly short, probably a fairly decent cable. So we're doing 3 amps, that's pretty good. I'm not feeling any warmth yet from this. Let's keep going. We're dropping a little bit more voltage. Well, that's pretty decent actually. 4 amps out of here. That's pretty impressive actually. 18 watts. I'm just going to leave this for a minute and see if it can sustain 4 amps. Alright, it's been about 3-4 minutes later, and we're still holding up here. Top of this vent's getting a little warm. It hasn't been on that long, so the whole enclosure is not that warm. Cable's probably a little bit warm. This cable's definitely not designed to carry 4 amps, maybe an amp or two at the most, but I think we'll, at the risk of damaging things, we'll just keep going. Let's see what happens, see if it cuts out or, you know, 5 amps. Look at that, that's pretty. The claim that this will do 7 amps is looking more and more realistic. I'm not going to try to pull 7 amps out of one USB port. This is as much as I'm going to try to pull out of this one port, because it's definitely not designed, each one of these ports is not designed for 5 amps. So we're doing 23 watts out of this right now, which is pretty amazing. I can't imagine the voltage is that stable anymore. It's probably fairly noisy. We might load it and have a look at that later. I think now it's maybe time for a teardown. So let's figure out how to get this thing apart. Okay. So I did drop this earlier, and there's a piece of plastic. I think this piece broke off. So anyways, it appears that there are some screws here, and here. So I'm just gonna assume it's gonna be a Phillips. So I don't want to have to peel this off. I'm just gonna try to get at them underneath like this. And looks like my assumption was correct. These are little Phillips screws. Four of them, it appears to be. Okay, I feel something loosening up here. Yep, this bottom portion comes out. And does this just slide out? Well, let's see if this comes off. There's this broken piece here. It's a very short little USB ports here. It looks just like a switch mode power supply. Let's see if we can get this off somehow. Looks like this just clips on here, so let me see if I can unclip it here. Hopefully without breaking it, this might be somewhat useful to me. Okay, there's one. I can squeeze this now. Oh, that one broke. Probably should be using a guitar pick. You know what? I don't know if this is actually essential to taking this apart. There's one more here. Let me get a guitar. Okay. Let's put this down a little bit more. Okay. Come on, one more here. Does not want to come out. There we go. Okay, so then we have this case like this. Oh, that does come out now. It's much easier. Okay, so we have just our offline supply here. Pretty chunky little transformer. Looks fairly straightforward. There's appears to be no interference filter on the primary side. Couple ICs here, which is interesting. Let's take a look, see if we can see what this one here is. Okay, it's upside down. The TC730. I'll have to look that up. And TD6530. So this is probably just some offline switcher chip. We have a couple bulk capacitors here. They are in parallel. We have our bridge rectifier. Pretty basic. For the output we do, we have let's see, 2 output capacitors. So let's see if they're in parallel. I think they are, I'm not sure. I think there's definitely going to be some ripple on here. We have to see what this other IC is. Although, that's interesting. It looks like it's probably like a MOSFET or something. As the pins are all basically joined, except for this gate probably. This is probably a gate here. So that's kind of interesting. Secondary side switching, or is it the secondary? I would have assumed the transistor was built into this chip here, because this is the secondary side. So this may be some sort of reference voltage reference slash transistor. We'll look it up. I'm not sure. Anyways, let's see if these output capacitors are just in parallel. Yeah, appears they're just in parallel. So it does output quite a bit. However, there's no inductor to quiet the ripple. On the secondary side, two bulk primary capacitors and 2 secondary. You have your capacitor here, interference capacitor. Fairly simple. Pretty nice heavy duty current carrying traces here. This is definitely not going to be super low ripple by any means. And maybe we'll take a look at this. We'll maybe try to load it live. Since I am using an isolation transformer, I can hook the scope up. So we'll put some load on it, and we'll look at the ripple on the scope, see if it's significant, which I'm sure it will be. Definitely built down to a cost. They could have done much better job. I assume that this is before looking at the scope, so let's take a look. Okay, so we're all hooked up. We have the scope hooked up to the ground and the 5 volts. I'm fairly confident that's 5 volts here. We also have it hooked up to the load here, dummy load. And I'm going to slowly be increasing that. The dummy load is using an isolated supply just through a switch mode power supply. I hope it is. It's a Samsung. And I'm going to be using, is it a Samsung? Yeah. And I'm going to be using my isolated supply for this too. So the 2 isolated supplies, we shouldn't have a problem. All right, let's turn it on and hope for no sparks, because I don't have any protections built in here now. There we go. Took a minute, just like last time. So it wasn't the load that took a minute, it was just the supply. All right, now let's actually zoom in a fair bit more. We're down to 500 millivolts per division right now. Let's go a little bit more too. We can already see under zero load, quite a bit of noise. Yeah, look at that, that's terrible. 600 millivolts of noise thus far, no load. So let's put a little load on here. Okay, it's 200 millivolts and 300 milliamps. Sorry, 300 milliamps. We're doing about 550 millivolts of noise. So half a volt of noise. Not too good. Not looking too good for this thing. Let's go up to an amp. Okay, at an amp, what do we have? At an amp, we have 757 millivolts of noise. Let's turn this off and take a look here. See if the board allows for some improvements. See, these are all marked as capacitors, so you would hope there'd be like some sort of inductor marked here somewhere. All right, I'm back. So tempted to make some changes here. Instead of these little 1010 volt capacitors, I had this, what is it, a 3300 cap here. Yeah, it's only 6.3 volts, which is a little bit low. It's obviously like still a volt over the maximum voltage we're expecting out of the supply. I also cut a little slot here and put in this inductor as a filter. See if we can filter out some of this. So with the bigger cap and the inductor, we'll see how much better it'll make things. I'm pretty sure it'll make things at least somewhat better. So I'm going to solder this up, and then we can look at it under the scope again. It's a pretty long cap, but it actually just fits in here like this, so we should be good. So let me put this together, and I'll be right back. All right, back again. I got this stuff soldered up, so we get this much larger capacitor, and we have this 10 microhenry inductor, just in line with the in series with the 5 volt power trace here. And so another thing I'd like to note is okay, so according to this printout here, this one is capable of the 5 volt 2.1 amp. So, and these are all usually half amp, 1 amp, 1 amp. But then if you look at this, it's just one single trace. So really doesn't matter. Let's see. So the positive is going to be this one. So it's not even, yeah, it's the one closest to the output capacitor is actually this top one here, and the further one is down here. So if we're going to be actually dropping more voltage down here if you're loading this up here, so it should probably be at the top end instead of the bottom end, but whatever, it's just for, you know, advertising. It doesn't really matter. So looks like there is another spot for a capacitor down at the bottom there. Is there yeah, not put in there, so that's interesting. So that may be why there is that. So let's load this thing up and see if it's any better. All right, so we're hooked back up here. We got the probe on. We're hooked up to the electronic load. Let's take a look at the scope again. No explosions. There's our 5 volts. Okay, let's zoom in on it a little bit. 2 volt, 1 volt, 500 millivolts here. All right, so at idle, we're sitting at 850 millivolts of noise still. So that's, oh no, hold on. Our load was on, so let's cut that down. So we're at we're about 500 millivolts of noise now. So could be worse. So now let's load. Let's do an amp here. So we are at half an amp. We're at 1 amp here. So we're about 660. So it's still not very good. Let's load up to 2. All right, we're at about 2 amps here. So we're doing about 940, so it's really not looking that much better. So that's still quite a lot of noise. So I'm not really sure why it's not making more of a difference, but yep, not looking too good for this supply in general. Okay, so I was looking into this a bit more, and it's interesting. The closer I get to all this primary switching stuff here, we have some issues with a lot of noise. If I probe up here, there's almost no noise, like 100 millivolts, something like that, even under like 2 amps load. So then the further down we get down these traces, we have a bunch of noise probably from all this switching stuff. Okay, so I'm going to probe in a few different areas. I'm going to start here, and I'm going to work my way down a little bit. And we're going to be, I'll have about 1 amp load. And we can watch a scope and see how the switching noise goes up. Okay, we're currently sitting at 500 millivolts noise. And I'm going to make sure to keep this probe wire away from this. And see what we have here. So right now, it's 120 millivolts of noise. Oops. 120 millivolts noise. No load. Okay, let's load it. Right, we're at 1.05 amps. So nothing basically more visible. 160 millivolts noise. Okay. Now I'm going to probe at the very top USB jack here. Okay, we can see we already have 940 millivolts noise here. And this isn't even really down in the switching area. So we already have substantial more noise. And here's a bit further down. So quite a bit more as well. 1.2 volts of noise. So it seems as though we're picking up just a lot more noise from the traces the lower on we go. So I guess another thing to do would be to try to probe the load and see how much noise we have transferred onto the load. Okay, so right now I actually have the probe on the load. And the switching noise is actually not that significant. Oh, there we go. If I push down harder, maybe about a little more than a half a volt. So it seems there's just, let me move this cord. Yeah, about a half a volt. So it seems that it's largely due to just switching noises. So it's probably not that bad of a power supply. Especially after these changes. Too bad I didn't try to measure it before that. Potentially some isolation could be cut. Let me turn this off here. You could potentially cut some isolation channels here. This is probably good enough. I'm not sure how it's picking up this noise, but yeah, there's definitely some noise being transferred in from this supply here. from the switching into these traces down here. Probably just act like some sort of antennas, pick up some stuff. Maybe adding some capacitance down here like they have the capacitor on the other side marked. Flip this over. Right here. So maybe I'll try to add a capacitor here, see what it does. I added a capacitor that was already on the board here. It was just one of the same output capacitors that I took off. I tested it. It tested near 1,000 microfarads anyways, so I added it here. And that actually makes a big difference. So let's take a look at the scope again. Okay, so now I'm actually going to be probing right down at the last USB jack. So this is where we were seeing a lot of noise before. And look at that. We're doing 80, 100 millivolts of noise now, okay? That's under no load. So let's increase the load. We're doing half amp. We're doing 1 amp right now, and we're at only 160 millivolts of noise. So that capacitor down there made a big difference, and then the filter I put on, well, I don't know how big of a difference it made because we didn't check closer to the output capacitor before. We were checking down by the rail voltages where the USB connector is plugged in. So I'm just increasing the current output here, or sync, and we're at 1.75 amps, 2 amps right now, and it's great. It's doing 200 millivolts. I think maybe we'll, keep losing the probe here. I think we'll go up to 4 amps again, maybe 5. I don't want to burn anything out after putting work into this, but you can see the voltage is dropping now. And this is this is on the other side of the load, so we're not getting any line drops. We're at 5.1 amps right here, so not too bad. You can tell it's just from not enough capacitance, and there's some weird drops every once in a while. But anyways, that's pretty good. At the source here, we're doing 4.9 volts RMS at 5 amps. So let's just keep going. Okay, we drop out before 6. So actually, once it's beefed up, the supply is not bad at all. Just if anything, I think adding a capacitor where it was missing down there maybe made the biggest change, and then we added some filtering and a much larger bulk capacitor on the output. So with those changes, supply seems fairly decent now. So this left off capacitor they left off was apparently pretty important to the noise just right on these rails. You know, we saw before, once we got off to the load, a lot of that noise had vanished. I don't know if it had dissipated somehow, but at the load it was gone. So it wasn't a big a problem. I put on a 10 microhenry inductor in series with the power. Well, that got kind of warm under 5 amps. And then a 3,300 microfarad capacitor as the final output capacitor. In between them we have the inductor. So with those changes, it's probably a fairly decent supply now. So you know, the supply probably wasn't terrible, but without this capacitor, the rail voltage we were seeing was fairly noisy. I wouldn't want to use it for anything without at least this, and this is just added bonus, I guess. So this is probably fairly capable currently. Alright, just having a look at the data sheet here. This is the only one I could find, Jing Da Tong company apparently.
So it's obviously all in Chinese, and at least we have the universal language schematic here, so we can translate that. But then we get this overlapping here, so we can just copy and paste it. So it looks probably like a fairly basic offline converter chip. Um, some various protections. Um, you can see here that uh, if we wanted better efficiency, we could use the voltage reference and some isolation back to the primary side, back to the chip. But that's only for higher efficiency. So you don't, it does not required to have that. And in their schematic, they don't show that actually being added either. We just have the auxiliary winding sensing the it's going to sense a voltage drop when there's loading and to try to regulate that way, which actually does a fairly good job of that. So another thing we didn't see though is any sort of EMI filter. Um, as far as I could tell, there was really nothing. Some chips they vary the switching a little bit, so it spreads the EMI a little bit, which actually complies from what I've read. But I don't. It doesn't look like this one does it. So unfortunately, it probably creates a bunch of noise. But I'm not too concerned with that because I don't really have too much sensitive stuff here. So um, that's a look at the datasheet.